Okay, ladies and gentlemen, let's go ahead and take a look at Pascal and a little binomial theorem. Now, among other things, we need to have a basis for what we're talking about. And the basis for this idea comes from the following. If I have x plus 2, well, that's a binomial, okay? We have one piece, we have two pieces. So everything we're going to deal with binomial is talking about two pieces. Now, if I just have x plus 2 and that's all raised to the first, that's no big deal. But as soon as I start dealing with x plus 2, the quantity squared, well, now I need to FOIL that out, and that becomes x squared plus 4x plus 4. And then I start taking a look at x plus 2 cubed. Well, that's really going to end up being x squared plus 4x plus 4 times another x plus 2. So I end up with x cubed. So give it away, give it away, give it away. So I get x cubed plus 4x squared plus 4x plus 2x squared plus 8x plus 8. And if I simplify all of that down, I come up with x cubed plus 6x squared plus, we got 12x plus 8. Something in that ballpark. Now let's double check my math on this. X cubed and 4x squared and 4x. And I come up with 2x squared. And I come up with 8x plus 8. Okay, so it begins to work out very, very nicely. Now, we could continue on with this, but the problem is, you'll notice I had to pause here and make sure that I can even get to x cubed, and I had to double check that I had my stuff right. Well, what if I had something like x plus 2 to the 7th power? Okay, x plus 2 to the 7th power is going to be quite a bit. But what if I had something like x plus y to the 7th power? Now I really have all sorts of stuff, because even if I have x plus y squared, that's going to be x squared plus 2xy plus y squared. Okay? And so this is how I would end up with my coefficients. So we have all sorts of challenges that when we start putting these binomial pieces together, that we run into a little bit of trouble. Now, one of the things that's going to help us with this is a thing called Pascal's triangle. And Pascal's triangle is going to be super helpful as far as coming up with some of our coefficients. Now, if I were to deal with x plus y cubed, well, in this case, we want to take x plus y, x plus y, x plus y. And I'm going to end up with x squared plus 2xy plus y squared. And then I'm going to multiply that by x plus y. So I'm going to get x cubed plus 2x squared y plus y squared x plus yx squared plus 2xy squared plus y cubed. Now, if I simplify any of this down, I have some x cubed on this end. I have some y cubed on this end. I have an x squared y here and an x squared y here, meaning 3x squared y. Just because they're y, x squared, y, we can turn around commutative property multiplication. These two, I'm going to come up with 3xy squared. And we start to see a pattern develop. That pattern that begins to develop is the exponents always add up to, in this case, 3. Because what I really have is I have a sneaky y to the 0 here, or a sneaky x to the 0 here. 3 plus 0 is 3. 2 plus sneaky 1 is 3. 1 plus 2, 3. 3 times 0, or 3 plus 0, 3. So we end up with always the power of 3 because everything is cubed. Now you'll notice when I was doing the cubes here with the x's, doesn't always quite work out because we have these numbers. If numbers were a variable by themselves, you would have this idea of number cubed, number squared, number, and number to the 0 power. And you number. And so it would still work out like this, but because they're numbers themselves and they can be further simplified, we don't quite see the pattern when it's a variable and a constant. But with variable and a variable, we definitely see it. So the pattern that we begin to see is x and y, then x squared, 2xy, y squared, x cubed, plus 3x squared y, plus 3xy squared plus y cubed. And what you'll notice is you end up with these patterns. And the pattern is easily broken down by Pascal's triangle. If I have 1, which is just a constant, no variables, no nothing, I have 1 as a coefficient. But as soon as I take x and y, I have 1x, 1y. Then I have 1x squared, 2xy, 1y squared, 1x cubed, 3x squared y, 3xy squared, and 1y cubed. Well, there's a pattern that begins to develop. And that pattern is any given 2 create a middle term. So in this case, 1's go down the side like a flying V, and any of the internal terms are created by adding those 2 adjacent terms. So 1 and 2 makes 3. 2 and 1 makes 3. Now, again, to the next one, let's go to the 4th power. My coefficients, I'm going to have a 1x to the 4th on the beginning and a 1y 4th on the end. But in the middle, I'm going to get a 4. 3 plus 1 is 4. Here, I'm going to get a 6. Here I'm going to get a 4. So if I were to attempt to fill in all the x's and y's, I'd have x to the 4th. This would be x cubed y to the 1st because they have to add up to 4. This would be an x squared y squared. This would be an xy cubed. You'll notice they switch as they move across. And a y to the 4th. Moving on down, I'd have a 1, a 5, a 10, a 10, and a 5, and a 1 at the end. Moving on down after that, I would have a 1. I would have a 6, a 15, a 20, a 15, and a 6 and a 1. And you'll notice very quickly I can come up with all of the coefficients that go with an expanded binomial, whether it's to the 0 power, the 1st power, the 2nd power, the 3rd power, the 4th, the 5th, the 6th. So in this case, it would be a plus b to the 0 power, which means it's just a single 1 value because anything raised to the 0 is 1. Here's a plus b to the 1st, a plus b squared, a plus b cubed, a plus b to the 4th, a plus b to the 5th, a plus b to the 6th. That is using Pascal's triangle. Now, with Pascal's triangle, we come up with a number of things, and we'll deal with that in the next video.